Hi, everyone. Thanks for coming to my talk. It's my pleasure to present this work on the automated analysis of TLS 1.3. So Cas and I did this work at the University of Oxford. I was his PhD student there, and currently I'm at MPI for Software Systems in Germany. And Sam and Tyler work at, or are PhD students at the Royal Holloway University of London, and they did part of their this work there as well as at Mozilla for their internship. So let me situate our work for you first. So TLS, as you might know, has a long history of being broken and fixed, and our contribution to this field came about in the year 2015. So the best part of it was spent to analyze TLS 1.3, and in October the cool stuff started to emerge. So what we do are formal methods, in particular the symbolic verification of security protocols, and we consider our work to be complementary to the provable security work that's being done. And here are 4 great papers cited. So the difference between our work and theirs is that they do a deeper analysis in a way, but we do a broader one where we cover all the different modes of TLS 1.3 and their complicated interactions with each other and with the old protocol modes. So this new version of TLS 1.3, is designed to be more efficient than TLS 1.2 with the 3 new modes. So the zero round-trip time handshake mode basically allows clients to encrypt some application data for servers when they meet again or when they resume a session on a different connection. So this encrypted message can be put in the client hello message, and so is sent immediately on a return visit. The pre-shared key or PSK mode is a way for both clients and servers to use pre-shared keys that can be established either out of bound or by running the TLS 1.3 protocol. And they're used as building blocks to compute session keys more efficiently, so less computation is needed. Lastly, the delayed client authentication mechanism is a way for servers to only authenticate clients when they really have to. So, for example, you can imagine a client browsing through a public portion of a website, and then they try to access some secure or sensitive resource or log into a secret part of the website or private part, and only then does the server need to authenticate them. So our goal was to improve the security of TLS 1.3 by analyzing its specification, by using state-of-the-art formal analysis methods and tools. And what we focus on are interaction attacks. So we assume that cryptography is perfect or black box. So basically that it works as it should. So either you have a key and can encrypt, decrypt, and sign messages with it, or you don't, so you can't possibly do it. And we assume that the attacker is a Dolev-Yao style attacker, which means that he can position himself in the middle of a connection and then eavesdrop on, tamper with, and inject messages, as well as corrupt or compromise the long-term secret keys of protocol participants that aren't directly involved in the session that is under attack. So the interaction attacks, by this I mean inadvertently added vulnerabilities that are exploited due to some sort of composition of these different handshake modes. So when we were building a model, what we first did was infer a client and server state machine from the specification. And as you can see here, if you start at the initial state for the client, this is the client state machine, what the client can do is either start a new session by doing the C1 transition. He can, on a repeated visit to a server, he can try to initialize a pre-shared key mode. which then branches out into two different modes. One is the Diffie-Hellman ephemeral mode, where a Diffie-Hellman ephemeral secret is used for forward secrecy. And the pure PSK mode is used if forward secrecy is not an issue. And it actually features even less computation than the PSK DHE handshake. And lastly, there's the known configuration mode, which is basically the zero round-trip time mode. So on a repeated visit to a server, a client can use this server configuration message that he got from the server, with which he can use a part of it to encrypt application data immediately for the server without going through the ordeal of setting up new TLS session keys. And then there's the question of client authentication. So it's nice and uniform. This is why it narrows, the state machine narrows there. So the server may ask the client to authenticate it, then they may or may not do so. And the rest is not relevant for this talk. So as you can see, it's a complex beast, and there can be any number of clients and servers engaging in any number of sessions. So we really needed unbounded verification here. Unbounded in terms of both breadth and depth. When I say breadth, I mean the number of concurrent sessions or parties. And unbounded depth, I mean the number of repeated handshakes and retries due to parameter mismatches. So we needed a tool, of course. So we encoded our model for use in the Tamarind Prover, which is a state-of-the-art tool for automated protocol analysis that's built at ETH Zurich in Switzerland. And it supports loops, which is important for the repeated handshakes and retries. It supports branches, which is very important for all these modes of the protocol that need to be verified. And it also has state-of-the-art Diffie-Hellman symbolic Diffie-Hellman support, which allows us to actually consider the core security in the TLS protocol, which is based on the Diffie-Hellman exchanges. However, this tool requires considerable user interaction for such a complex model. However, we use Tamarind to verify the core properties of TLS 1.3 revision 10 as an authenticated key exchange protocol, which means that we prove that the session keys are secret with the forward secrecy included. So for experts, we don't allow our adversary to compromise the semi-static Diffie-Hellman exponent of the server. So this is why this is a full kind of perfect forward secrecy here. Then we have the authentication properties. So servers always properly authenticate to clients, and clients, if required and they want to, properly authenticate to servers. And the handshake messages cannot be tampered with without at least one honest participant noticing this. The last thing that we wanted to check is whether it was safe to include the delayed client authentication mechanism in revision 10. And for this particular version of it, which is the initial proposal, which came about at IETF 9.3, which is this unrestricted variant, Tamarind says no. So we managed to use Tamarind to fight an attack on this unrestricted version of the delayed client authentication mechanism. This unrestricted version works as follows. So basically, a server can, after any handshake, require a client to authenticate. Okay, and if a client decides to do so, then there you have the C-auth red transition. So the attack that Tamarind finds goes something like this. Imagine Alice, who's a client of a bank, and she wants to connect to her bank. Okay, so she wants to access her bank account. Unfortunately, Charlie at evil.com sent her a phishing email, and it looks nice. It's Alice falls for it. And then she actually decides to connect to him and establish a PSK by using TLS 1.3 revision 10 with the unrestricted delayed client authentication mechanism. So there's the they establish this PSK1, pre-shared key. And Charlie, let's say, knows Alice's bank, mybank.com, which Bob is running. And he would ideally like to access her bank account and then transfer all of her money to him. So what he does is connect to mybank.com and establishes PSK2 with Bob. Okay? So far, so good. These two keys are different. These two sessions are different, so and completely legitimate. There's been no funny business yet. But let's look at the second stage. So imagine that Charlie now cuts the connection to Alice. And then Alice comes back trying to resume it on a different connection. And she sends her client random value NC in her client hello. She generated a fresh value NC. Charlie then reuses, he's a client in this other session, right? The PSK2 session. He decides to resume the session with Bob by reusing this NC value. And Bob says, okay, sure, let's resume the session. And he generates a server random value of NS for his server hello. And Charlie constructs his server hello again by reusing this NS value this time. So you might have noticed the session hash values in the bottom there that are filling up. So the session hash is basically a hash of a partial transcript in a session. So in this particular case, it has NC and NS. However, these have been made the same in both sessions. And this is actually enough to make the session hashes in both sessions the same. This is a very unfortunate trait of revision 10. Oh, right, I forgot to say the client finished messages also go through no problem because Charlie knows PSK1 and PSK2, so he can build these confirmation messages. So in this second part, again, there hasn't yet been anything terribly illegitimate, but the session hash has been made the same by Charlie in both sessions. And this is what Charlie will now leverage to steal Alice's money. So now he tries to log in at mybank.com as Alice, which prompts Bob, who has no idea who he's talking to, apart from the fact that that person is claiming to be Alice. Bob now requests authentication from whoever is on the other side, and it's Charlie, of course. Charlie now needs some sort of excuse to ask Alice for her authentication. Let's say that she clicked on something at evil.com, or maybe she tried to log in to her account. Of course, that's a bogus form that Charlie made. And Alice says, sure, I mean, I should probably authenticate now if Charlie says so. So she sends him her certificate, a public key certificate, as well as a signature over the session hash and the certificate. And now the problem, so Charlie couldn't possibly forge this message himself because he doesn't have the secret key of Alice. He couldn't forge the signature. But he could reuse it entirely and relay it to Bob as an authentication package because the session hashes are the same. And these are the only things that are supposed to bind the signatures to their respective session, which obviously didn't work here. So when Charlie says, give Charlie all my money to Bob, then Bob will say, sure thing, Alice. So we posted our analysis results and this attack to the TLS mailing list at the end of October 2015. And the responses we got were quite positive. Let me read a few for you. Nice analysis. I think that the composition of different mechanisms in the protocol is likely to be where many subtle issues lie, and analyses like this one support that concern. Thanks for posting this. It's great to see people doing real formal analysis of the TLS 1.3 draft. This is really helpful in guiding the design. This result motivates and confirms the need to modify the handshake hashes to contain the server finished when we add post-handshake authentication. So the thing here is that the session hashes would already have been the same if they contained the server certificate. So if you remember, on the one side we had the server Charlie, and on the other we had the server Bob. And their certificates, of course, differ. So if already the server certificate was in the client signature, then this attack would have been prevented. However, what the TLS working group actually suggested was to add the full finished message, which contains, which is basically a confirmation of the full transcript, not the partial transcript, the full transcript, into the client signatures, because, I mean, into the session hashes, which would transitively also include them in the client signature. And this would help, of course, bind the client signature to a session, as the name session hash actually implies, of course. So our attack shows that the initial proposal for delayed client authentication is incomplete. It also shows that it's strictly necessary to bind client signatures to server certificates. And as I said, the working group proposed to include the full transcript in the form of the finished message to the signature, to bind the signature to the client signature to sessions. And this proposal was actually merged in revision 11, which prevents our attack. To sum up, this was the first and, to the best of our knowledge, only comprehensive analysis of the new TLS 1.3 modes and their interactions. And this story actually has a happy ending, because we managed to successfully verify revision 10 by using Tamarin. And we also used Tamarin to find an interaction attack on the delayed client authentication mechanism. And the proposed fix was verified and also included in revision 11. For our future work, we would like to update our model and to revision 13, and then verify that, perhaps with respect to a stronger adversary model and with some new properties that we have in mind. And let me just say that we believe that our work is just one piece of the puzzle, just like Felix said, actually. And we would like to continue being part of this larger concerted effort of different approaches to hardening TLS 1.3 that we believe all of them are valuable. Thank you.
Questions?
Hi, so it's pretty fascinating what you can find with tools like Tamarin. The attack you've described, at least in the slide, seems somewhat complicated and uses phishing.
Right.
And the kind of things you can do with phishing are sort of by themselves quite complicated and powerful. So I'm curious if there's a way to abuse this kind of weakness that you found without phishing.
Well, as long as you have a reason for Alice to connect to a malicious entity. That I mean, she doesn't know, of course, that the entity is malicious. If there's anything other than phishing that you can use, then yes.
Okay, thanks.
Hi, so I'm Shinichiro Matsuo from TLS Consortium. So could you tell me why you choose the Tamarin to this analysis?
Sorry, why?
Could you tell me the reason why you choose the Tamarin as a tool?
So the reason is it had everything we needed, right? So it had inductive reasoning, so we could deal with loops. It had non-monotonic state, which is one of the reasons it was built in the first place, so we could deal with branches in all these modes, right? And I guess the third reason I brought up was the symbolic Diffie-Hellman support, which is actually the second of the two most important reasons that it was built.
Thank you.
I guess.
Is it correct to say you can actually do it without phishing? Because I think actually if Alice just visits any arbitrary website, the attack will still work. So as long as the website is malicious.
Sure, that's true.